All right, a popular application of Bernoulli's equation is the case where you have a column of fluid, like the column that you have on your table. That column is called a Mariotte cylinder. It's just the name of it. Probably after somebody that I haven't really researched. So when you have a small, and I say small column, I'm not talking about this column is not the size of a skyscraper. This column would fit in our classroom. Okay, maybe it's a graduated cylinder. Maybe it is the Mariotte cylinder that's specialized for this. Maybe it's a pipe in the wall. It doesn't matter, but it's not something that's enormously tall. Okay. Anyway, so you've got this thing full of a fluid. So there's the fluid top right there. And maybe it springs a leak, but it gets a little hole in the side. What's going to happen to the fluid in this column if it gets a little tiny hole in the side? You think it's going to shoot out like this? What kind of motion is that? Projectile motion. Dun, dun, dun. Yay! Okay, so let's talk about this. Now, if the cross-sectional area of this column, so here's the cross-sectional area of the column, so that's the area of the fluid in the column. If that A1 is much, much bigger, and technically much, much bigger is 2 greater than signs, much, much bigger than A2, so this is the little tiny hole in the side. If it's much bigger than A2, then if you look at the continuity equation, A1V1 is equal to A2V2. If A1 is really big, A1, and A2 is really small, A2, then tell me about V1. Has to be really small. And what about V2? It has to be really big. It has to be so big, or it becomes so much bigger than V1, that V1 is approximately 0. Now you are equipped with pressure change indicators. Do you know what they are? Your ears. Okay? So, is there a pressure difference, a significant pressure difference from the top of the column to one of the holes? No, you don't feel your ears pop as you stand up, right? You don't even feel your ears pop as you go downstairs, most of you anyway. Okay? So, is the pressure of the atmosphere at the top of the column different, significantly different than the pressure on either of the little openings on this pipe? No. Because we're talking about something that's not the height of a skyscraper, then the pressure at the top of the column, so P1, is approximately equal to P2. Now, if we put all this together with all these conditions together with Bernoulli's equation, that was P1 plus 1/2 rho V1 squared plus rho GY1 is equal to P2 plus 1/2 rho V2 squared plus rho GY2. We put that together, P1 and P2 are the same, so when I subtract P1 from both sides, it's a wash. So those don't matter, they're the same, right? And then what about V1? V1 was approximately 0, so doesn't that term become 0? Alright, so that leaves me with rho GY1 is equal to 1/2 rho V2 squared plus rho GY2. Now what can I do to both sides? So the rho can cancel out. Alright, so now let's solve for V2. So subtract the GY2 from both sides. So multiply by 2 on both sides, and then we're going to divide. So that's Torricelli's equation.